Hello everybody, welcome to the third lecture on compound stresses under module 2 of the subject strength of materials, subject code 15CV32, which is common for both civil engineering as well as mechanical engineering sciences. And I am Dr. S.V. Venkatesh, Professor, Department of Civil Engineering, PES University, earlier PES Institute of Technology, Bangalore. Now, in the previous two classes, we have discussed about the introduction of compound stresses, state of stress at a point, general two-dimensional stress system, and principal stresses and principal planes. And today we will look at what is Mohr's circle of stresses and how to get the stresses on different planes. To recall what we had discussed in the last two classes, I'll run through the PPTs that we had used earlier. So we had discussed about the introduction, this is the slide. Then we had discussed about the state of stress at a point and how to get the stresses on different planes. Now, transformation of plane stress, we had discussed about this and I had derived the expression to obtain the normal stress on any given plane, that is this equation given by this equation, as well as the shearing stress given by this equation. Now, we have solved few problems on this, how to find the normal stresses and the shearing stress on a given plane, and then we discussed about principal stresses and principal planes, where we use these equations to get the principal stress maximum as well as minimum and the principal planes by using this equation. Now, the maximum shearing stress was also discussed, where we use this equation to get the maximum shearing stress and the plane on which the maximum shearing stress occurs by using this equation. And the average shear stress is given by this, which would be the stress that's going to be acting on the plane where the maximum shearing stress occurs. We had discussed few problems related to principal stresses and principal planes. These problems we had discussed. We will also see how to get this or solve this problem by Mohr circle. Before that, we would see what is Mohr circle. We had discussed these two problems Then now today we would discuss about how to get this Mohr circle. First, we will start with the derivation for obtaining the Mohr circle. This equation we had derived this, which gives you the stress on any plane, inclined plane in a plane stress block, okay, which is given by this equation. This is the normal stress on any plane, and this is the shearing stress on the corresponding plane. Now, let us take these two equations and then see how to get the equation for Mohr circle. So, what do we have here is sigma n, or we can also represent this as sigma x dash, which is equal to sigma x plus sigma y by 2. We had derived this earlier also, plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. Now, we would square this equation on both sides, so we would have this as sigma x dash whole square. I would get this on the other side of the equation, so this would have as minus sigma x plus sigma y by 2, and I am going to square this. This square equals this sigma x minus sigma y by 2 square cos square 2 theta, plus when I square this term, I am expanding it as well. When I square it, tau xy square sin square 2 theta, plus I would get this as 2 sigma x minus sigma y by 2 cos 2 theta sin 2 theta. Now, remember this equation. Now, we also had the equation for tau, which is given by tau is equal to minus sigma x minus sigma y by 2 into sin 2 theta plus tau xy cos 2 theta. Again, squaring this equation, we would get this as tau square, which is equal to sigma x minus sigma y by 2 whole square into sine square 2 theta plus tau xy square cos square 2 theta. Now this as a negative sign, so we get this, the next term as negative, minus 2 sigma x minus sigma y by 2 sine 2 theta into cos 2 theta. Now this equation and this equation are the equations that I am going to use in the next step. Look at this. This equation, we have got it from this equation. When after squaring we get this, while this is for the normal stress on any plane, this is the shearing stress on the same plane. When I square this, I am going to get this. Now I am going to add this equation and this equation, and we will get the solution as given by this. So for that I am going to erase this. Okay, what do we get? We have this, so this term is what I am writing it as it is. Then I am going to add this to this, so we would get it as plus tau square. This is equal to, if you observe, when I get this term, it is sigma x minus sigma y divided by 2 whole square into cos square 2 theta. When I add this to this, I would get this as sigma x minus sigma y by 2 whole square. This cos square theta plus sin square theta is what we get. We can take that as 1. As you know that sin square theta plus cos square theta is 1. So we would combine these two and we get this only. Then next term is this, where I will get it as tau xy square. Again we have here as sin square 2 theta, and then when I add this I get plus cos square 2 theta. So sin square 2 theta plus cos square 2 theta will be equal to 1. So whatever term that is going to be left for that is tau xy whole square. Then the next term, this is plus 2 times sigma x minus sigma y by 2 cos 2 theta sin 2 theta is what we get. This, when I add to this, this is with a negative sign, so these two terms will get cancelled and we will be left with only this. This is what we are going to get. Okay. Now look at this equation. I am going to erase the remaining equations so that I can use the space for writing. Okay. Look at the equation that we have got. This equation is of the form, the equation for a straight line, which is x square plus y square equals r square. This is the equation for a circle. Okay. So if I compare this equation with this equation, I can say that this equation is also an equation for a circle, where the term x corresponds to sigma x dash, and this is the average shear stress, so I can write this as average whole square, plus y corresponds to the tau, that is the shearing stress, tau square, equals this r corresponds to this, which is sigma x minus sigma y by 2 whole square plus tau xy whole square. So this equation is similar to that of a equation of circle, so we can use these terms to get the Mohr circle. Okay. Now let us go back to the PPT and we will see that, see, look at this, this is the equation that I have derived just now. This corresponds to this equation where we have this as x square plus y square equals r square. Then see, as I discussed about it, sigma average is given by sigma x plus sigma y by 2, and r, which is a radius, is given as root of sigma x minus sigma y divided by 2 whole square plus tau xy whole square. Now if I take this equation, this is the equation of a circle, and if this is plotted on a graph where the abscissa is the normal stress and the ordinate is the shear stress. This is easier to see if we interpret sigma x and sigma y as being the two principal stresses and tau xy as being the maximum shearing stress, then we can define the average shear stress sigma average and a radius r, which is given by this. Okay, we will be using this equation to draw the Mohr circle. Now this we have got it, which I have just now derived this equation. This is what we have. Now here the circle is centered at the average stress value and has a radius r equal to the maximum shearing stress as shown in the figure below. Now if you look at this figure here, the x axis is the normal stress, which is represented as sigma, and the y axis is represented as the shearing stress tau xy, and the average shear stress will be the midpoint of the circle and the radius will be equal to the maximum shearing stress. So we get this, and the maximum value on the sigma axis or the x axis corresponds to the maximum principal stress, that is sigma 1, and the minimum corresponds to the minimum principal stress, that is sigma 2. Now how do we get this for a normal stress block? Let us take a normal stress block as we had done earlier. So the stress block sigma x, the positive sign, which is tensile in nature, so this is sigma x. Then sigma y is also, I am taking it as positive, this is sigma y, and we had taken tau xy as indicated here. This is the positive sense of the shearing stress, what we have taken earlier. Okay. Now if I take this into consideration, now the sigma x is the positive axis that we are going to take and sigma y is the positive axis. Both of them are tensile in nature, so that would be positive. When we are plotting it on the x axis, the sigma x, if it is tensile, we have to plot it on the positive side of the axis, and sigma y will be if it is tensile, we have to again plot it on the positive x axis. Now coming to shearing stress, very important, what we have to take is the shearing stress, the sign convention for shearing stress, the sign convention. So this is how we are going to take the sign convention for shearing stress. Say if the shearing stress is acting on the y axis, the sign convention is, if it makes the body, if the shear stress tau xy, if it is going to rotate the body in the clockwise direction, we consider this to be positive. Remember this, if the shearing stress acting on the plane, if it is going to make the block rotate in the clockwise direction, we would consider that as positive. Whereas if the shearing stress is going to make the body to rotate in the anti-clockwise direction, we would consider that as negative. This is the sign convention that we are going to use for plotting shearing stress. Okay. Now, so if I take the same block, you can see in this PPT the diagram that is given here. To get this, okay, let me use the blackboard to indicate what we are going to get. So I will erase this, we have already seen this. So let us use the same stress block and see how to plot the Mohr circle. Okay, so let us take x axis and y axis. So along the x axis we are going to plot the normal stress, along the y axis we are going to plot the shearing stress. Now according to this, sigma x is positive because it is tensile. So I will go on the x axis and I will mark a point which corresponds to the stress that is acting, that is sigma x. Now on the sigma x axis, the shearing stress that is acting would make the block to rotate in the anti-clockwise direction. So anti-clockwise rotation, because of the shearing stress, we have to take it as negative. So, and the shearing stress is measured along the y axis, so I have to come down by this, and this distance is what we are going to measure, and this corresponds to tau xy, which would be negative, and that is acting on the face where sigma x is acting. So this is sigma x and corresponding to that we will plot that. So, this is denoted as x. Now, similarly, we take this phase sigma y is tensile, so it is positive. So, we will plot on the x axis this which is corresponds to sigma y, Now, if I look at the shearing stress acting on this plane where sigma y is also acting, this would make the body to rotate in the clockwise direction. So, clockwise rotation, because the shearing stress is taken as positive. So, I have to plot this above, which would be equal to the same thing, which is tau xy. So, this is the y axis. This is corresponds to the y axis. Now, what are the ordinates of x? X ordinate is sigma x minus comma minus tau xy, whereas the y ordinate is sigma y comma plus tau xy. These are the ordinates that we have. Now, if I join these two lines, okay, this is going to cut the x axis or the normal stress axis at a point which I will call it as C. Now, with C as the center and the radius either Cx or Cy, we would draw a circle passing through these points. So, something like this. This is how we are going to get the circle. Okay. Now, this is called as the Mohr circle. Now, the point corresponding to the x axis, the maximum and minimum, would, if I consider that as point A and point B, the value on the x axis corresponds to the maximum value of the normal stress, which we denote it as sigma max, whereas the B point corresponds to the minimum principal stress, that is sigma minimum. Now, to get the principal planes, now as we can see here, this is what we have the block, the normal stress sigma x and sigma y and tau xy, and when we rotate this, the plane on which the maximum principal stress is going to act, okay. So, this is sigma max, the normal stress on this plane, and this corresponds to theta p, which is the principal plane, Now, this one is measured with respect to sigma x, okay. So, the same theta is corresponds to when we measure it with respect to sigma x, which is the sigma x axis. Sigma x axis is this line corresponds to this values. So, we measure this angle, which we would get this as 2 theta p. 2 theta p corresponds to the maximum principal plane, okay. And if I measure this from here, this corresponds to 2 theta p minimum. This is the maximum plane and this is the minimum plane, okay. So, and the other value that you need to know is this value, this distance would be equal to sigma x minus sigma y by 2. This is the value that we get, which is the average value, and the center, okay, would be acting, okay, the center, and we can also get the sigma max value as equal to sigma average plus r, and sigma minimum is equal to sigma average minus r. Now, what is this? The average value is nothing but sigma average. We have got this as sigma x plus sigma y by 2. This corresponds to the center of the Mohr circle, that is this one. This is nothing but sigma x plus sigma y divided by 2. So, to this value, if I add the radius, which is Ca, I would get this as sigma max. Similarly, if I want to get the minimum, so it is sigma average minus r, r is again Cb. So, C is sigma average minus Cb, I would get the minimum value, minimum principal stress value. Okay. So, I hope you have got you have understood what is Mohr circle and how to draw Mohr circle for a given stress block. Okay. Now, look at the PPT. We have the Mohr circle, whatever just now I explained is given here. Okay. So, the maximum principal stress is given by OA. OA gives the maximum principal stress. OB corresponds to the minimum principal stress. Then O, this point is the stress value that is acting, which is corresponds to x, which is equal to the ordinate equals to sigma x comma minus tau xy, whereas this point corresponds to the value sigma y plus tau xy, and this is half of sigma x minus sigma y. Okay. This is how we need to plot the Mohr circle. Okay. Look at this diagram, okay, which would give us what is the plane on which the principal stresses is acting. We can either measure it with respect to the x axis as theta p. Now, the maximum principal stress that is acting and the minimum principal stress that is acting is given from this diagram, and the angle at which it is inclined, that is theta p, is also given. So, this is the plane on which the principal stress is going to act, and this plane with respect to vertical will also be at the same angle, that is theta p, as indicated earlier on the board. Okay. Now, let us see how to get the value of the normal stress and the shearing stress on any given plane, For that, let us go to the blackboard again. So, let us see how to get the normal stress on any given plane. Say for example, I take this plane and which is inclined at an angle of theta. I need to find out what is the normal stress acting on this and the shearing stress acting on this. Now, to get that, what we need to do is, the angle that we are measuring, which is theta, is with respect to this plane where sigma x is acting. Now, this corresponds to the, if I look at the Mohr circle, it corresponds to the line Cx. The angle at which we need to find out the normal stress and the shearing stress is theta. So, I have to draw a line from Cx, okay, from Cx I have to draw a line, okay, which would be equal to 2 times that of theta, which is 2, this angle corresponds to 2 theta. Now, this line, wherever it cuts the circle, that corresponds to the normal stress and the shearing stress that is acting on that plane. Now, this one, this value, whatever we get from the origin, corresponds to the normal stress acting on this plane, which is sigma n, and this value from the x axis corresponds to the tau x dash y dash. That is the shear stress that is going to be acting on this plane. So, normal stress is going to be normal to this, which is sigma n, this value, and the shearing stress that is going to be acting is tau x dash y dash, or we can also write this as sigma x dash. That is the normal stress acting on any given plane, which is inclined at an angle of theta. Now, this point, the other point, would represent the normal stress acting on the plane which is differing by 90 degrees to this, that is theta plus 90. Okay. So, that is how we get the normal stress and the shearing stress on any given plane, and the maximum principal stress, maximum principal stress and the minimum principal stress, and the inclination of the maximum principal plane. This is how we get using the Mohr circle. I hope all of you have understood this. Now, let us continue this. Now, look at the PPT. Here you can see the stress block, which is here given by this, and this gives you the maximum principal stress and the minimum principal stress, and this is the plane at which it is acting, which is theta p. Now, this is the inclination of theta where we want the normal stress acting when it is inclined at an angle of theta, this is theta. So the forces that is going to be acting is given by this, and how to get it is what I explained just now. Okay, let's now take a example. Now this problem we had solved it earlier also by using the formula to get the maximum principal planes, maximum principal stresses and the maximum shearing stresses. So we will take this. So in this you can see how to draw the Mohr circle for this stress block. Okay. Now here sigma x is equal to 50 megapascal, which is positive because it is tensile, whereas sigma y is negative because it is compressive with the value of 10 megapascal and shearing stress as a value of 40 megapascal. Now let's take this first. Now x axis, it's the principal stress or the stress axis, normal stress axis. Y axis is the shearing stress. Okay. Now to get the Mohr circle, we would first plot this, which is 50 megapascal, it is positive. So from the origin we move by a distance which is equal to 50, indicated by this 50, which is corresponds to this 50, which is positive. Then this shearing stress which is acting on this plane would make the body to rotate in the anti-clockwise direction, and as we discussed the sign convention for shearing stress, if it makes the body to rotate in the anti-clockwise direction, we should take it as negative and the value is equal to 40. So this 50 whatever we have measured, that is OF, from F go down by a distance of 40, which is equal to this. So we get the point X. This is the point which we get. Okay. Next, look at this. This on this plane we have the normal stress which is acting, which is 10 megapascal, and this is compressive, so it is negative, which we have to plot it onto the left of the origin. From O you move by a distance 10, which is indicated here. So we get to G point. Then the shearing stress acting on this is equal to 40 megapascal, which makes the body to rotate it in the clockwise direction. So when the shearing stress make the body to rotate in the clockwise direction, we take that as positive. So move up from G by a distance 40 megapascal, that's what is indicated here. This is equal to 40. So we are moving up. So we get the point Y. So we have this point X, we have this point Y. Join these two by a straight line which would cut the X axis at a point C. This would be the point which we have to take it as the center of the circle, with C as the center and Cx or Cy as radius. Draw a circle. Now this circle is nothing but the Mohr circle. Now this circle would cut the X axis at 2 points. One is at point A, the other one is at point B. Now if I measure the distance of A from the origin O, OA gives me the principal stress and which is positive, and OB gives me the minimum principal stress which is negative. Okay. Now if you look at this, the average the average normal stress is sigma x plus sigma y by 2. In this case sigma x is positive 50, sigma y is negative, that is 10. So you get this as 20, and this is what is the average shear stress, average normal stress, which is 20. Okay. And CF is this, which is equal to 30, and the radius is given by this CF, which is 30, and this Fx, which is equal to 40, that is the shearing stress, so which is equal to 50. Now from this, as I told you, sigma max is equal to OA, that is O to A, so that is equal to OC plus CA, OC plus CA. CA corresponds to the radius and OC corresponds to the average shear stress. We had found this, which is equal to 20 plus 50. If I measure this distance, we get this to be 70. That is the maximum normal stress, which is the principal stress. And to get the minimum principal stress, it is OB, the distance OB, which we would get it as OC, now average normal stress, minus BC. minus BC. BC minus OC is what we get, which is equal to minus 30. These are the principal stresses, maximum and minimum. Okay. Next, to get the planes on which the principal stresses is going to act, which is very simple. This angle corresponds to 2 times the principal planes. So, tan 2 theta p is equal to Fx by Cf, or Cf, which is equal to 40 divided by this distance is 30. So, we get this as 2 theta p equal 51.3 or theta p equal 26.6, and this is the angle theta p, and this is the maximum principal stress that is acting, which is corresponds to 70, and the minimum is minus, so it is compressive. So, we have found the maximum principal stress, which is given by this, minimum principal stress, which is given by this, and the plane on which it is going to act, which is 26.6, and this is how we get the principal stresses. Okay. Next, now the same problem, how to get the maximum shearing stress and the angle at which the maximum shearing stress is inclined. Okay. The maximum shearing stress would be equal to the radius of the Mohr circle, because the y-axis represents the shearing stress. So, if I measure this radius, which is tau max, which is 50, we get this, that is the radius r. Okay. Now, to get the angle of the shearing stress, okay, that would be equal to the angle which we measure it from the line Cx to this point. So, this entire thing is going to be equal to 2 times the plane on which the shearing stress is going to act, that is 2 theta s. So, this is the angle that we get. So, 2 theta s. Now, we can also get that theta s as theta p, which we have already found, plus 45, which we get as 71.6. That is what is indicated here. 45 plus theta p, this angle would be 71.6, and the stresses that is going to be acting would be the shearing stress is 50, which is the maximum value, and the corresponding normal stress that is going to be acting would be the average stress, which is given by 20, which is nothing but OC. OC would be the normal stress that is going to be acting on the plane on which the maximum shearing stress is going to act, which is given by this 20, and this is what we would have got when we use Mohr circle. Now, the same problem we have solved it earlier by using the formula. Now, you can compare the values that we have got earlier also. I would show you that by going back to my PPTs, whatever we had presented earlier. So, this is what we have done earlier. So, you can look at this diagram. See, this corresponds to the same figure what we have done, what we have taken today. Now, here the principal planes is 26.6 and the maximum, and the minimum is 116, which corresponds to what we have got today. The value for the maximum principal stress is 70 and the minimum principal stress is minus 30, which we have got today also. Then the maximum shearing stress, this is the equation that we had used, and we got it as 50. Today also by using Mohr circle we got it as 50, and the shearing stress, the plane shear, the maximum shear stress plane is given by this minus 18.4 and 71.6. So, here what is indicated is minus 18.4, whereas in the Mohr circle we had indicated as 71.6, which would be 90 degrees to this axis. Okay. So, the average normal stress is this, which is 20, which we have got it in the using the Mohr circle also. So, I hope all of you have understood how to get the Mohr circle, what is the derivation for Mohr circle, how to draw the Mohr circle, and how to take the values from the Mohr circle. Okay. So, one example we have solved. We would look into the next example. This is the first example. We would look at the next example. Okay. Here we have a stress block wherein the sigma x value, sigma x is tensile, which is positive, which is given by 100 megapascal. Sigma y is also positive, which is 60 megapascal, and the shearing stress acting on this is 48 megapascal. We have to determine the principal planes and the principal stresses, the stress components exerted on the element obtained by rotating the given element counterclockwise through 30 degrees. So, here we are finding out the maximum principal planes, principal stresses, and we are also trying to find out what is the normal stress acting on any plane which is inclined at 30 degrees, okay, when we rotate this block by 30 degrees in the counterclockwise. Now, how to get this? Let us see. So, remember this, the sigma x is positive because this is tensile, sigma y is also positive. Now, shearing stress, look at the shearing stress axis. The shearing stress acting on this plane, which is corresponds to sigma x, would make the body to rotate in the clockwise direction. So, it has to be positive, and this one which makes the body to rotate in the anti-clockwise direction should be negative. Let us look at this. So, what we have got here is the Mohr circle. So, how to draw this? So, you have x axis, draw the x axis and the y axis. Now, from the origin, take a point 100 megapascal on the x axis, okay, and this is positive. So, move to the right from the origin, okay, by 100, right. So, that is this point, this f, OF corresponds to 100, right. Okay. Next, the shear stress acting on this plane would make the body to rotate in the clockwise direction. So, we have to take it as positive. So, measure above the x axis along the y axis by what value? 48 megapascals. So, this OX corresponds to 48 megapascals. This should be 48. So, you can see here x, the ordinates is 100 comma 48. So, we get this x point. Similarly, you take this, that is sigma y, which is measured as 60, which is equal to measured from O, the origin, to this point. This value corresponds, this value is equal to 60. Then the shearing stress that is acting here would make the body to rotate in the anti-clockwise direction. So, anti-clockwise rotation is negative. So, we have to go down by what value? 48. So, we have gone down by 48. So, we get this point which is y. So, the ordinate of this point is 60 comma minus 48. So, we get this point and this point which is x and y. Join this by a straight line. This line is going to cut the x axis at point C, with C as the center and Cx or Cy as radius. Draw the circle. This is what we are going to get. This is the circle that we are going to get. Now, once we get this, to get the maximum principal stress, the point A corresponds to the maximum principal stress, measured it from the origin, that is O. OA corresponds to the maximum principal stress, which is given by 132 megapascal, and OB corresponds to the minimum principal stress, which is given as 28. Now, both are positive, that is tensile in nature. Now, to get the principal planes, measure the angle from C to X to the x axis, which corresponds to the 2 times the principal plane, that is 2 theta p, which is indicated here. Okay. To get the maximum shearing stress, it is the radius of the circle, okay, which is OC to this point, which or C to this point, which is nothing but 52 megapascals. Okay. So, from this diagram, we have got the principal stress, the maximum principal stress, the minimum principal stress, the principal planes, we can find the principal planes, and the minimum principal, the maximum shearing stress value, which is equal to 52. This is what we have got. Now, we can also determine from this what is the average, that is sigma x plus sigma y by 2, which is 100 plus 60 by 2, which is 80, corresponds to the point C. OC corresponds to the average normal stress, which is equal to 80, the radius, which is 52, which is the maximum shearing stress. Now, we have found the maximum principal plane, principal stresses. So, let us look at that. Okay. So, 2 theta p corresponds to the principal plane. So, this is what we have, the stress block, 2 theta p. So, to get that, tan 2 theta p equals xf divided by cf. If I do that, I would get that as 2.4. So, 2 theta p corresponds to 67.4 and theta p corresponds to 33.7, measured clockwise, because we are this is the axis and we are measuring it in the clockwise direction. So, we rotate this by the same angle, which is 33.7, and we get this block. The stresses that is going to be acting would be the maximum and the minimum principal stresses, which we have got it as sigma max, which is equal to 132 megapascal, and sigma minimum, which is equal to 28 megapascal. So, that is what we get from this. Okay. Now, that is what is indicated here. How to calculate it is shown using the Mohr circle. Now, how to get the plane on which the maximum shearing stress is going to act. Okay. Now, we had drawn x and y, the Mohr circle, we had got point A, point B, we had got this, right, okay, x and y, and we had got this. Now, to get the component after rotation by 30 degrees, point x dash and y dash is what we are going to get. Now, 30 degrees means in the Mohr circle it should be equal to 2 times of this, which is 2 into 30, which is 60 degrees. And so, from the xy you get an angle which is equal to 60 degrees and draw a line. This line is going to cut the Mohr circle at 2 points, which is corresponds to x dash and y dash. X dash and y dash corresponds to the stresses acting on a plane which is inclined at 30 degrees, rotated in the anti-clockwise direction. So, that is what we need to find. So, 2 theta p is 60 degrees, we have drawn this line which is x dash and y dash. So, if I measure the distance OK, this gives me the normal stress acting on the plane which is rotated by 30 degrees, that is sigma x dash. And similarly, if I measure OL, this gives me the normal stress acting on the plane which is at 90 degrees to the 30 degrees plane. Okay. Now, the distance k x dash would give me the shear stress that are acting, which is equal to L y dash also. So, that is what is indicated in this diagram. We have rotated this by in the anti-clockwise direction by 30 degrees. So, this is the block that we get. The normal stress that is acting, sigma x dash, corresponds to this value, that is OK, which we would get it as 48.4, and this value sigma y dash, which would be at 90 degrees to this, which is also positive, and it is 111.6 megapascal. The corresponding shearing stresses that is going to be acting, very simple. So, we measure this value, which is x dash k, and this is above the x axis in the positive y axis direction. So, that means this stress would produce a clockwise rotation. So, that is what is indicated here, which is 41.6. This is nothing but this is tau x dash y dash, which is equal to 41.3, and it produces a clockwise movement. Whereas this one L y dash would produce and it is below y, which produces a anti-clockwise rotation. So, we will get the shearing stress like this. So, this is the shear block on which or this is the shear block which is rotated at 30 degrees, and the normal stress and the shearing stress that is going to be acting is what we have obtained. Okay. So, this is what we get when we do this, the values, the 48.4, 111.6 megapascal and 41.3 megapascal. So, this is how we get the values of the principal stresses, the principal planes, and the normal stress and the shearing stress on any plane which is inclined at an angle theta. Okay. That concludes my talk on compound stresses. What we have looked at is, if I go back and see what is the syllabus prescribed by the university VTU. So, I have covered all the portions. See, we have looked at introduction, then state of stress at a point, general two-dimensional stress system, how to get principal stresses and principal planes, and how to draw Mohr circle and how to obtain from Mohr circle principal stresses, minimum as well as maximum, then principal planes, the maximum shearing stress, how to obtain the maximum shearing stress using Mohr circle, as well as we have derived the expressions to get the values of maximum principal stress, minimum principal stress, then maximum shearing stress, the angle at which or the plane on which the maximum principal stress is going to act is also we have got. Okay. So, I hope with this lecture you would be able to understand what is compound stresses is and able to solve problems to get the normal stress as well as the shearing stress on an inclined plane. Thank you very much. I would stop my lecture here. I thank everybody for this. Thank you.